Umesh Waghmare.
Yeah.
It's on quantifying the intrinsic flexibility of crystalline materials.
Thank you.
Yep.
So, thank you, Chairman. I first want to thank Tony for the invitation and many other things you will see in this talk. I thank Natalie for perfect support in terms of organization and her team, and also His Highness for the funding that allows us to come here for this workshop. So the topic is actually an example of curiosity-driven research, which was stimulated from interactions with Tony and his colleagues in one of such meetings here in Waghmare as well as in Bangalore. So idea is quantifying the intrinsic flexibility of crystalline materials. Flexibility is a term which is very commonly used from biology to material science to sociology. And in this case, we are going to restrict to mechanical flexibility and basically propose a phonon-based theory of deformation response in the context of MOFs. So first, I thank my collaborators, a PhD student Meha Bogra, who is now moved on to faculty at Shiv Nada University, and Andrew Goodwin from Oxford, and Tony, who is here with us today. So motivation behind this talk was a very beautiful perspective written by Tony and his collaborators along with Tom Bennett. The perspective was on interplay between defects, disorder, and flexibility in metal organic frameworks. And very beautifully, it was shown that there are two axes here, as you will see, the disorder and flexibility. And on the one end, you can have ZIF, which can take amorphous form, which is quite interesting, I feel. Unlike other amorphous systems, the density of this is higher than the crystalline form. And the other end is flexible ZIFate. With very similar chemical constituents, it forms a very flexible structure. However, the notion of flexibility itself is not so precisely defined, at least in my perception. So the purpose of this talk is to tell you what we propose as a quantitative measure of flexibility, and also its connection with amorphization of these crystalline forms. So one of the statements from the abstract of this perspective article I'm quoting here, although such nanoporous materials were traditionally seen as rigid crystalline structures, like brittle structures, there is growing evidence that large-scale flexibility, the presence of defects, and long-range disorder are not the exception in MOFs, but the rule. So it's a very commonly seen property, and that's why our focus in this work is only on MOFs, but the ideas should apply to other crystalline systems as well. So this is amorphous and this is flexible, and we will like to propose a phonon-based theory for this type of spectrum of properties. So what are the questions that we wish to address in this work? First is, what is flexibility of a crystal and what is its quantitative measure? Second, is it related to rigidity, which is a very important property in physical description of systems, which is a consequence of broken continuous symmetry. When a liquid becomes crystalline solid, it develops rigidity, which is basically the elastic rigidity. And is flexibility related to that? And you will see the intuitive notion does say that it's related, but we will highlight what precise connection between the two is existing there. Next, mechanical flexibility involves response of a crystal to stress or pressure. So what is the origin of flexibility in MOFs as opposed to other simple crystals? Why are MOFs more flexible than other crystals? And how does it compete? Flexibility involves mechanism which can also compete with another possibility of amorphization, and that's also intrinsic to MOFs. And if these two involve change in the structure, both flexibility and amorphization involves distortions and changes in the crystal structure. Phonons is a natural language for such deformation because phonons are essentially structural excitations, and that's why we use phonon or spectral thermal signatures of these two ideas that we will refer to. In fact, the boson peak, which is very well known in glassy systems, we will show can also occur in MOFs. So one of the take-home messages are MOFs incipient glasses. It's possible, some of them. So I hope I convince you of this. So let me start with what is known about flexibility so far. And there are two works that I will refer to. One is by, again, Tony's group, Jim Tan's work in 2012, where low elastic moduli, particularly shear modulus in this case, was linked with greater flexibility of MOFs, because low modulus means there will be a large deformation for a given amount of stress. Right? That's one way to think about it. The second piece of work is little more quantitative, and that's related to this picture. On the left, you will see, although this is sort of from the engineering perspective, you take a sheet of a material and try to bend it, and the radius of curvature through which you can bend that sheet, this is decided by this simple formula, which involves a geometrical factor 2 by h, h is being the thickness of the film. And second factor is intrinsic to the material which makes that film, which is sigma y upon E. So sigma y is a yield stress of a material, and E is a corresponding elastic modulus of that material. Okay? So here is an Ashby type chart based on this work by Jeff Snyder and his collaborator. So as you can see, the chart basically is dominated by non-crystalline systems in a way, because you will see this is the figure of merit for flexibility defined by them as sigma y by E. And you will see crystals and ceramics, basically metals are here. They fall between 10 raised to minus 4 and 10 raised to minus 2, which means they are very less flexible in comparison with rubber, natural rubber, or even graphene or carbon nanotubes. So what our goal is to understand flexibility in this window of systems, where they have a different mechanism of being flexible, and that's what we will uncover here. So let me move on. Just before I move on, I tell you it's possible to physically interpret this figure of merit of flexibility. Sigma y is the yield stress after which the material deforms in a non-linear manner. Okay, so sigma y upon E, basically you see E is the slope of this sigma by strain curve, stress by strain curve, and sigma y is where it breaks if it's a brittle material or starts bending. So this ratio basically tells you the largest possible elastic strain a material can accommodate, and that's a reasonably good description of flexibility as well. So what we will be doing is to focus on this window, and let's see where we go. So why phonons? I already explained that if there is an application of stress or any perturbation to a crystal, there are changes in the structure as a deformation response, and that type of structural changes we are broadly classifying in three classes. One involves flexibility on the left, which means the crystal symmetry doesn't change during this response. The second is structural phase transition, where generally there is a sudden change in the symmetry of that crystalline system. And third is amorphization, where there is a complete loss of long-range order, basically no translational periodic symmetry left. So of course, there are stable versus possibly unstable phonons which are involved in these phenomena. I will describe to you these ideas in the next few slides. And of course, the symmetry of phonons which are relevant to these three phenomena are very interesting too. For example, in flexibility, the phonons must have the symmetry of the perturbing field. For the structural phase transition, the phonons should have a symmetry different from what is called as identity representation of the symmetry group, or symmetry lowering distortions. And amorphization, you will see, requires something special about phonons to lead to that type of instability. So let's move on. So let me first talk about rigidity, which is linked with the intuitive notion of flexibility of crystals or solids. So if you think about liquids, they possess longitudinal phonons, meaning the sound waves can propagate through liquid, which are longitudinal waves. Whereas they have continuous translational and rotational symmetry, means liquid is invariant under these symmetries. And as a result, you can't really have transverse sound waves in liquid. Okay, transverse sound wave basically means shearing of a liquid, and if you shear a liquid, it just flows. It cannot, so it doesn't have rigidity against shear waves, right? But once you form a crystal by freezing a liquid, you break that continuous symmetry, and there's a Goldstone theorem which says that the system will host transverse acoustic phonons as well, and that develops rigidity in the system. And Phil Anderson was a big proponent of these ideas. And here is a phonon dispersion. Basically, it's very similar to electronic band dispersion, where y-axis is the frequency of vibration, and the x-axis is inverse wavelength in different directions of a crystal. So rigidity, which is basically the finite slope of this phonon branch, as you see the TA transverse acoustic branch, which is present only in crystals but not in liquids. Okay, so crystals exhibit discrete translational symmetries, and as a result, this rigidity is given by linear dispersion of these phonons with wave vector omega equals CQ, and C is the velocity of transverse sound in this case. Okay, so this is the background of rigidity, which has a very fundamental origin in terms of Goldstone theorem. So structural phase transition, the second idea, basically is a fairly well understood concept, which are mediated by soft phonons, which involve symmetry lowering of the high temperature phase, and that phonon displacement basically constitute the order parameter or the measure of ordering in the low temperature symmetry broken state. And they can be first order or second order phase transition. If you look at very sort of standard structural phase transitions, I'll quote here ferroelectric phase transition, you will find there are unstable modes here, which are basically imaginary frequency, means omega squared is negative in this case. And those constitute the signature of structural instability, which give rise to a structural phase transition. And if you look at experiments, of course, they will also show anomalies in those specific phonons when the phase transition occurs at that temperature. Okay? So phonons really are the key degrees of freedom to these phenomena as well. And lastly, amorphization, the third aspect of this mechanical response. One goes from crystalline, perfectly ordered phase to amorphous phase, disordered phase, which preserves possibly the local structure and local coordination, but it disrupts the long-range ordering in a material completely. And of course, in experiment, you will be able to see this in X-ray diffraction pattern, where you will go from discrete peaks in the of a crystal to very broad single peak in the amorphous phase. So what we will show now is this can be caused by a flat band of phonons which are unstable. Okay, that's sort of is another message you will get from this talk. Flat bands are very popular in twisted bilayer graphene, but I want to highlight to you that in twisted bilayer graphene, the electronic bands are flat in a very small region in reciprocal space. Okay, so flat bands usually give you localization in real space, and localization of electrons in twisted bilayer graphene is not much. Actually, it's very long, 30 angstrom to nanometers. So whereas here, flat bands means you really have disorder possible in every alternate unit cell. So lastly, these phonons are also relevant to thermal fluctuations and specifically boson peak, which is a feature in glassy systems where if you look at the specific heat, which deviates from the Debye laws, T-cube behavior of specific heat at very low temperature. And if you plot C specific heat by T-cube, at very low temperature, you see another peak or excess specific heat, what is called. And that is usually arising from vibrational modes, which are present at fairly low frequencies, which are different from the linearly dispersed vibrational modes in crystals. Okay? So it appears that flexibility and amorphization of MOFs should be connected to each other and through this phonon language of phonons. And our prediction is actually you should see a boson peak in MOFs as well. And indeed, that prediction is, we realized that experiments were already done, and we could show that indeed these peaks exist in MOFs. So we'll be working with two MOFs in this work. One is MOF 5. And again, many of you have seen this before, so I'll quickly go through it. It's a FM3 bar M space group symmetry. It has octahedral secondary building block units. Organic linkers are basically benzene rings, as you will see here. The second MOF we work on is ZIF8. Again, these are motivated from the work Tony has done over a number of years. And this has I4 bar 3M symmetry, soda light structure, and it has a fairly interesting structure of ZnN4 tetrahedra, which are corner connected to 4 imidazole rings, and with a cube octahedral pore. So flexibility, let me start intuitively. What we want to say is flexibility is the ability of a solid to accommodate homogeneous deformation or strain through internal structural arrangements without a phase transition or loss of structural integrity, okay, or without losing the symmetry character of the system. That's intuitive definition of this, and now we will translate soon into a very quantitative definition. First, let me explain to you what we mean by internal structural arrangements, and there we sort of again compare it with a liquid. If you look at atomic scale structure of a liquid on the left, it has P1 symmetry, means there are no, in the sense of a space group of a crystal, if I think of it as a periodic system. And when I compress a liquid, basically the atoms in that liquid rearrange themselves, with very little energy cost. Or when I apply shear, they also again flow. So flowability of a liquid is linked with the fact that you have infinitely many symmetry-preserving internal degrees of freedom or atomic motion, and that's why you get high flowability. However, liquids have no special periodicity, and hence they are not rigid. When we think about a crystal, and on the left is liquid, which is known for flowability. So the definition of flexibility we introduce is analogous to flowability of a liquid. So if I look at this solid and I apply stress to it, this has a lower symmetry and it can adjust itself. This angle can change, the buckling angle, and in response to external deformation, and that's what is called internal structural rearrangement in response to external stress. Whereas this crystal, which has a very high symmetry, it has no internal degree of freedom to adjust in response to external field. If you compress it, it has to stay on the same, atoms stay on the same Wyckoff sites. Okay, so here flexibility is 0 in our notion of flexibility. So flexibility in a way counters rigidity. Rigidity is a consequence of broken continuous symmetry, and in our notion, flexibility tries to reduce that rigidity to 0 if you go to infinite limit to a liquid in some sense. Okay, yeah. So let's look at our measure of flexibility. So it is basically ability to accommodate deformation epsilon, the strain in the system, through symmetry-preserving atomic displacements, without undergoing phase transition or integrity. So our parameter is defined here. It's basically the denominator of it, this is the energy cost of uniformly deforming a crystal, okay, without letting it to adjust internally. So imagine you applied stress at a very infinitely fast pace. The crystal will deform instantaneously, and that's the cost in the denominator. The numerator is now you allow that crystal to relax, okay, for a given applied mechanical stress, and then it lowers that energy. So the fractional reduction in energy by internal structural relaxation of the elastic strain energy is flexibility in our notion. So it's linked with energy scales rather than length scales and deformation. Okay, so here is a pictorial view of it. The top panel shows that if I start with a crystal structure with 0 strain deformation or 0 strain, I apply a strain, this is the way that crystal will deform. And if I allow it to relax, it doesn't change its structure because there is no internal freedom. Whereas the bottom figure, you will see I start from this undeformed structure, I deform it. Well, it has a room to adjust the buckling angle, and then it changes back to a relaxed state, and that has a non-zero flexibility. So that's sort of the way we are looking at flexibility. And then we use first principles calculations to determine flexibility of a variety of crystals, and you will see here, this is in response to hydrostatic strain. You will see ZIF8 falls very close to 1, and zinc oxide, which is a very simple crystal structure, wurtzite, with only one internal structural parameter, has very low flexibility because when you apply compression, only 1 degree of freedom gives rise to that. Okay, so this sort of fits the intuitive picture we have about flexibility of these solids. what makes one material more flexible than the other? And here is basically the expression of flexibility written in terms of bulk moduli, where you will see the bottom is basically bulk modulus corresponds to infinitely fast or affine deformation, and the numerator is the reduction in that by relaxation. So you will see that in MOF5, actually the elastic cost is higher than, lower than the elastic energy cost of ZIF8. But what changes is basically this n gives you the number of internal degrees of freedom which are relaxing to give you lower energy state for a given strain. And that's where ZIF8 wins. It has many more ways of adjusting internally and lowering its energy, and hence it is more flexible than MOF5. Okay, so this way we can also understand why certain crystals are more flexible. And you see here is again Ashby type chart where our measure of flexibility goes from 0 to 1, and ZIF8 falls close to 1, whereas zinc oxide is basically very close to 0. So I think, yeah, how much, do alert me when I'm 5-10 minutes before the time. Yeah, thank you. So we can also analyze this in a slightly more simple model picture, where we work with phonons in harmonic model, and then you see the energy is written as elastic energy as a function of strain, and this is the key term which gives you coupling between strain and the optical phonons, you knew. Optical phonons are the internal degrees of freedom of a crystal. Yeah? And then the last is the stiffness of bond, the optical phonon frequency squared. Yeah. So the key point is the coupling between strain, which are acoustic phonons. I explained to you that those are the ones which give you sound waves, and optical modes. So internal strain and deformation strain, they couple together to give you flexibility. Okay, so if you work out this expression, you will find out that this is the more by phonon contribution to flexibility. Now with this, we can even point out which vibrational modes are responsible for greater flexibility of a given crystal. And using this, we find that actually a very counterintuitive result. Typically, people used to believe that it's low frequency soft phonons vibrations which dominate flexibility. What we show is actually soft phonons and hard phonons, relatively hard phonons, have to work together to give you high flexibility. You will see this is ZIF8, and this phonon dominates. 36% of the flexibility comes from the intermediate frequency. This is the spring constant of a phonon, and low frequency modes typically contribute less, but they give much larger internal structural displacement. See, this is the key point I want to highlight here. Soft phonons help in large internal structural relaxation, giving you large deformation in length scale. But they cost very little energy. When you apply stress, that energy has to be absorbed by someone. And that role is played by the high frequency phonons. Okay, so you need, for a flexible material, you need a composite of hard things and soft things. Soft things will be basically giving you the flexible displacements, and hard things will be absorbing the elastic stresses that are applied to the crystal. Okay? So that's the sort of very fundamental understanding we derive from this analysis. And here is sort of a very graphical view of looking at this. On the left side, we are showing a kind of a bar chart, which color intensity says the dominance of phonons. And we have labeled the number of phonons by 1, 2, which sort of give most dominant contributions, and their displacements are atomic structural. These arrows basically tell you how the structure changes in response to this deformation and give rise to flexibility. Okay, so phonon modes relevant to flexibility in zinc oxide, you will see this is compressive flexibility, and this essentially involves different changes in the zinc and oxygen bond length, which are allowed by symmetry. And in ZIF8, there are many such displacements possible. The low frequency mode involves rotations of linker. Rotations, of course, are very low frequency vibrational modes, whereas intermediate frequency modes involve stretching of these bonds, you can see here. Okay? And those are the ones which absorb all the elastic stresses that are applied to the system. Okay, so we have, of course, access to a lot more information. On the left column, we have this modes which contribute to hydrostatic flexibility, and one on the right gives you shear flexibility, and you will see the shear one has lower symmetry modes, whereas these displacements maintain the symmetry of your lattice because hydrostatic strain doesn't break the symmetry. Okay, so all this fits beautifully well. So let me conclude the first part of this talk about flexibility. So we proposed a quantitative measure of flexibility which goes from 0 to 1 for crystalline systems. It's similar in spirit to flowability of a liquid. General relationship basically reflects that increased flexibility is linked with softer elastic moduli, which is consistent with what Tony's group had published earlier. Contrary to general conviction, if entails contributions from both high and low frequency vibrations, and high energy modes absorb the energy and stresses, and soft modes basically give you large deformations. That's the picture which comes out. And here is basically the idea that you break continuous symmetry of a liquid, you get a crystalline solid. But then solid can have continuous degrees of freedom to change its structure. Okay? Those remnant continuous degrees of freedom are what give you flexibility. That's the sort of take-home message from this work. I'll quickly go through amorphization and yeah. 10 minutes, okay, thank you. Yeah. I should be able to finish in time. So the second topic is amorphization of MOF5, and which is again a very interesting problem. These crystals become amorphous at unusually small pressures, just a few hundred megapascal, which is 100 times lower than typical pressures required for amorphization of other systems. So the question is and this is where we are going to say amorphization of a MOF is in competition with flexibility of a MOF in this case. Yeah. So the work, there was theoretical work as well a few years ago, which showed that there is a sharp change in volume at fairly low pressures to GPa, and first order transition is inferred. So what we will do is we will basically start with phonon description again. As I motivated, it is relevant to both flexibility and amorphization. On the left is a phonon dispersion of equilibrium structure of MOF5, and moment you compress it even by very little amount, it develops many unstable modes. And not only these modes are unstable, these modes are essentially very weakly dispersed, means their frequency doesn't depend much on the wavelength. And what this means is you can have basically unstable distortions or energy stabilizing distortion at any length scale and give disorder in the crystal. So that's what happens. And then we also look at those modes. Basically, the idea is where are these modes coming from? They must belong to some modes on the left-hand side, right? And that's what analysis we did. We basically are coloring them up. These are the modes in the stable structure of MOF5, which become unstable when you apply very small pressure. And those modes have symmetry, which is not, these modes don't preserve the symmetry of the lattice. Okay? So if those unstable modes will lower the symmetry, and that's what would happen. This is what sort of the picture of these unstable modes. They involve rotation of the BDC group. Some of them involve dispositioning of BDC group, and another is rotation plus shearing of the secondary building block units. All these processes are known to be very easily something which can be destabilized very easily. And then you will see this is the picture which develops. If I don't allow the structure to disorder, the energy cost is very high. This is pressure versus strain curve. And moment you allow the disorder to come in associated with these unstable phonons or distortions or disordered structure, the stress is released very rapidly at fairly small strains, and you see the pressure drops significantly as well. And that sort of is the reason why MOF5 amorphizes at very unusually low pressures. Okay? And this is the picture. You start from a beautiful crystalline form of MOF5, and then we consider sort of superperiodic structure and allow for distortions which lower the symmetry, and basically you develop amorphous phase at low pressures. So let me summarize. The vibrational spectrum exhibit low frequency flat optical phonons, and basically at very small compression you get unstable modes which constitute flat bands of phonons, and then any combination of those unstable modes is equally likely to destabilize the structure, and that's how you get amorphization through disordered state. Okay, I'll very quickly go through the last bit, which is about the boson peak, which relates to both flexibility and amorphization ability of MOFs. Basically, in the past, boson peak has been associated with glassy or amorphous systems primarily, and in some cases, it has been observed in crystalline systems as well, and they are sort of the causes given here. What we show is in MOF5 and ZIF8 both, you do see boson peak. This is specific heat by T cube, and it develops a beautiful sharp peak at very low temperatures. Very unexpected of a crystalline system. I guess not so unexpected of MOFs. And indeed, if you see experimental data here, this is what we said. It was a prediction we had, but luckily experiments already existed, and we could verify our prediction for MOF5 particularly. It satisfies what we have predicted from theory. So what is responsible for these boson peaks in MOFs? And that's where we do sort of more by more contribution to the excess specific heat. And what we find is in MOF5, most of the excess specific heat is caused by basically these two sets of phonons, which are grouped in A and B. And that basically is the phonon which involves displacements, again, of the linker molecule, translational motion, which gives rise to liquefying type shear distortions. And this is the set B. In ZIF8, again, there's only one set of phonons which dominates the boson peak. And that set of phonons is indicated here in this window. And basically, those phonons involve shear band-like distortions. And again, this is something which is known in amorphous systems. They deform in response to external stresses by forming shear band-type structures. So let me summarize. It's the coupling between low-frequency optical phonons in flat bands with acoustic ones give rise to both flexibility and they give rise to composite phonons. Means phonons are combination of strain and internal strain waves. And the details are system specific. In ZIF8, these are arising from shear band-like modes, whereas in MOF5, they involve rotations. And basically, the picture, the very easy to take home picture is as follows. These are the acoustic phonons, and this is optical phonons if they were not coupling with each other. So they would just cross each other. Okay? An optical phonon branch is flat. But moment they have a coupling possible, they have anti-crossing. So acoustic phonon branch drops in its slope from the initial one. And this drop is basically linked with the flexibility. And what we show is it's also linked with the boson peak and amorphization type ideas. I thank collaborators once again. And this is something, again, I must admit, came out of my interactions with Tony. I was not particularly involved in MOFs, but it's a beautiful science that I enjoyed working on with nucleation of ideas with interaction with Tony. And thank you all for your attention.
There are no questions yet from the audience, but from the online, but there are questions over there.
Very interesting talk, Umesh. Lots to think about. I have one problem with your analogy of these continuous degrees of freedom being broken and the liquid to solid, which I totally agree with. But I think the one thing that's missing is jamming. Mm-hmm. You know, because after all, you also have the same P1 symmetry in a glass, but you can't sort of deform a glass the way you could deform a liquid. And I think the analogy in the crystalline lattices may be one of topology. So have you considered, for example, instead of looking at a cubic topology like MOF5, have you considered looking at a pyrochlore lattice, or one of these lattices that have a lot of triangles and is very hard to basically frustrated against deformation?
I see.
Is for me the
thanks, Ram. Very good comments. I don't have a very clear response to your comment about jamming. But we did look at zirconium tungsten oxide, which is an oxide which exhibits negative thermal expansion. And what we find is the modes which contribute to flexibility are also the ones which are relevant to this rigid unit mode, which cause this anomalous negative thermal expansion there. Yeah? So about jamming, I don't have a clear idea. Yes, Vinay.
You always do such a thorough job. It's enjoyable. Thank you. My question is, I don't know how relevant it is, but polymer and organics have strain rate dependence, right, on the mechanical behavior. Do you see that in the composite system or at least the organic part of the MOF?
Okay. Okay, I see. So what I call composite phonons is basically sort of vibrations which involve combination of strain modes and also the internal strain modes. That's what we mean. But most of our analysis, Vinayak, is sort of a linearized analysis, and it doesn't really capture these other mechanisms which can kick in. We will like possibility of dislocations or faults which can come in the present picture. So flexibility is defined as really the intrinsic linear property of a material in this case, in manner very similar to the rigidity or modulus of a MOF.
The reason I brought that question is lately one of the collaborators at MIT, Ralph McFarlane, who uses DNA assembly, and he's now making macroscopic crystals, and now he's doing mechanical properties of those macroscopic crystals, and they do show there was strain rate dependence on mechanical.
I see.
So it's very analogous to MOF, I thought.
Okay, okay.
I'll send you some references.
Dan, the last question.
Thank you for a wonderful talk.
Thank you.
One question about I mean, initially when you describe this factor F, you say, let's just assume we compress the solid and then it relaxes. If you take that literally, then there's clearly a time delay between one and the other, which suggests that there is dissipation involved. And so would you expect enhanced sound damping in MOFs due to the coupling between the longitudinal modes, the acoustic modes, and the optical modes?
Okay, so damping will be expected if we have nonlinear interactions then, like the third order unharmonicity.
Sure.
And looking at the fact that you get unstable modes with very tiny compression means the Gruneisen parameters are very big. Yeah. And that means, yes, in MOF 5, we can say with confidence from our results that you should see anomalous damping of acoustic waves.
And have people looked?
I'm not sure. Yeah.
Okay.
But this may explain why the thermal conductivity of MOFs is very low. Also.
Okay.
Yeah. Generally, of course, these are not metallic, so all the thermal conductivity comes from phonons, and which is known to be a factor.
Thanks a lot.
Yeah. Thank you.
Thank you very much. Although I must say it hurts. Those MOFs are so beautiful crystals, and then all the efforts to make it amorphous. But despite that, a beautiful presentation. Thank you.
Thank you.